far we have seen how to change the variable and how to improve the sampling. So, among the changing the variable, so the idea was to go from a uniform distribution to a desired distribution of the random numbers. So, there looked like one, for example, we looked into how to get an exponential distribution from a uniform distribution of random numbers, but there is another distribution which is quite common and we have not talked about it, that is how to generate set of random numbers having the normal distribution or Gaussian distribution. So, basically the idea is I have a set of random numbers which is generated by my machine, which has a uniform distribution, and I go to or I transform them to another set of random numbers which has a normal distribution, or it is also called the Gaussian distribution, normal or Gaussian distribution. So, if I plot the distribution, so basically what it means is I have, so if this is my probability distribution function P x for a uniform one, and so I want to convert it to something like this for a like a Gaussian function. This is x. So, if we remember the recipe, so what we did it, okay, let me, for the sake of less confusion, let me just call it as y. So, if you guys remember what was the recipe? The recipe was we use the principle of conservation of probability, that is this equation, and where we set P x to this is equal to 1 for this particular case. And then what we did is we computed, basically we wrote x as a function of y to be the cumulative distribution of this new or the desired PDF. So, that is 0 to y prime, 0 to y, not y prime, sorry, the integral is 0 to y, and if I take my Gaussian distribution to be e to the power minus x square by 2. So, this is what is called a normal distribution, normal Gaussian distribution y prime dy prime. If you remember the conditions which this recipe or this function should have is that one, it needs to be integrable, but if you look at this function, we know that this is not possible to integrate analytically. The popular name of this function is, it is also called the error function. So, now we can't, so what it is clear from this is that we cannot, using this recipe, generate a Gaussian or a normal distribution of random numbers. So, but again, as I mentioned, there are several places in physics where these type of Gaussian distribution is followed. The system follows or the system can be represented by a Gaussian functions. There are many examples in physics. So, it is an important problem to need to solve. So, the question is, what is the way out? And so, in order to achieve this or to get this new distribution, so we have to use some unconventional technique, and the most popular and the popular technique which is typically used is called the Box-Mueller transform. So, what is done in Box-Mueller transform? So, what we need to do to avoid this particular route here is we need to, so far we were restricting ourselves to only one dimension. By one dimension I mean we are using just a single variable. So, there is only dx, and on the right hand side also there is only one variable dy. But rather than that, what we will do is now we will move to multiple dimensions, and there we can write down again the probability conservation in this form. Suppose we have a probability distribution function which is given by p y1, y2 and dot dot dot. So, it has n number of values, then the conservation equation now becomes the following. So, we have the probability distribution as a function of x, then we have this Jacobian matrix. So, x 1, x 2 dot dot in terms of delta y 1, y 2, like this it goes, and then I have d x 1, d x 2 and so on and so forth. So, these type of probability distribution functions, these are also called joint probability distribution functions. Because they depend on more than one variables, and this determinant here is the Jacobian determinant. It is called the Jacobian determinant, and the information it contains is the derivative of all x's with respect to y. So, basically it is a determinant containing elements of this form del x I del y j. So, now for our purpose, what that is to generate this Gaussian distribution. So, what we will do is we will use two variables. So, let me consider a joint probability function which is given by which is a function of two variables p x 1 x 2, which is equal to e to the power minus x 1 square plus x 2 square by 2. So, this is basically a two dimensional Gaussian function, or you can in terms of, since we are talking about probability distribution function. So, we can relate it as a two dimensional Gaussian distribution whose sigma is equal to 1. So, this is the distribution which I want, and what I have in my hand is the set of random number or my random number generator, which gives me the uniform distribution, random numbers having uniform distribution. So, what I do is to simplify this. So, I will switch to polar coordinates. So, what do I mean by that? So, by that what I mean is I rewrite x 1 and x 2 in the following form. Let x 1 is equal to y 1 cos cos y 2 and x 2 is equal to y 1 sin y 2. So, what is the relationship between x 1 x 2 and y 1 y 2? So, if I take the square of these two equations and add them up, so what I will get is y 1 square is equal to x 1 square plus x 2 square, and if I divide one equation by the another one. So, and what I will get is y 2 is equal to tan inverse x 2 minus x 2 by x 1. So, now I have got this thing, and what I will do is, if I call this as my equation 1, this is 2, and this set of equations we call it as 3. So, what I will do is I will take this 1 and 2 and I will plug it in this one, in this particular equation. So, what I will get is, in this case, if I do that, so I will get p y 1 y 2 as a function of dy 1 dy 2. This will be equal to, so my p x 1 x 2 from equation 2 is my this Gaussian distribution here, which is e to the power minus x 1 square plus x 2 square by 2. So, that is e to the power minus x 1 square plus x 2 square by 2, and then what I need to have is this Jacobian here. Since I have two variables, my Jacobian will be a 2 cross 2 determinant, and that will be given by del x 1 del y 1 del x 1 del y 2, and in the second row we will be having del x 2 del y 1 and del x 2 del y2, and then we have dy1 and dy2. So, just for our recap, let me just write down here the expression of x1 is equal to y1 cos y2 and x2 equals to y1 sin y2. So, if I evaluate these four derivatives and plug it in here, so what I will get is the following. This equation, the right hand side of this equation, we can rewrite in the following form: minus x1 square plus x2 square by 2. Then the derivative of x1 with respect to y1 will give me cos y2. The derivative of x1 with respect to y2 will give me minus y1 sin y2. The derivative of x2 with respect to y1 will give me sin y2, and the derivative of x2 with respect to y2 will give me y1 cos y2, and then I have dy1 dy2. So, what I can do now is, again, if you look at these two equations, so my x1 square plus x2 square, that is nothing but y1 square. So, I plug in y1 square here. So, I get e to the power minus y1 square by 2, and then if I evaluate this determinant. So, what I will be getting is y1 cos y2 square plus y1 sin y2 square, and together that gives me y2 square. Sorry, y1 square, and then I have dy1 dy2. So, this is what my probability distribution function will look like based on the new transformations that we have made. Now, these y1 and y2, these we need to generate from my random numbers which has the uniform distribution. So, in that case, so let us see what values y2 can take. So, y2, if you remember, so my y2 is tan inverse x2 by x1. So, basically what it means that my y2 will vary, or y2 can vary from 0 to 2 pi. So, how will I get these values, different values of y2 from the uniform distribution? So, what I need to do is multiply the random numbers from uniform distribution by 2 pi. So, this will then generate a set of numbers whose range is from 0 to 2 pi, uniform distribution. So, where this range is 0 to 1. Okay. And what will be the range of y1? y1 can take any value, because y1 is x1 square plus x2 square to the power half. So, in principle y1 can take any values ranging from 0 to infinity. So, now the question is how to relate y1 to a set of random numbers which lie between 0 to 1. So, to do that we make another assumption. So, what we say is, okay, let me define a new function which is u is equal to half y1 square. So, that implies y1 is equal to root 2 u. So, from here if I take the du will be given by y1 dy1. So, what I will do now is I will plug this into this expression. Okay. So, what will happen is the following. So, in this expression, if we focus on this particular term e y1 square, sorry, there is a mistake here, will be just y1, not y1 square. Sorry for that. So, what we will do is we will replace this part with this function. So, what I have is e1 square, e1 to the power minus y1 square by 2 y1 d y1. This I can write into e to the power minus u du. So, this is my new probability distribution function, and we have already seen that this is the probability distribution function is exponential, and for that we know x in terms of y, or in other words, in this case we can write down u as a function of x. So, basically what we need here is, what it means is that we need to have a set of numbers, random numbers, which follows the exponential distribution, and that we can generate again from a set of random numbers which has a uniform distribution and lying between 0 to 0 prime, 0 and 1, and if we call that as x prime. So, that we can write down as minus log 1 minus x prime. So, where my x prime belongs to between 0 and 1. So, if I plug in all these things now, so what I get is x 1 is equal to the number which I started off with is equal to y 1 cos y 2, and y 1 we know is given by root 2 u. So, what I need to do is basically take the log of, so it is minus 2 log 1 minus x prime, and then we have cos y 2, and similarly x 2 is equal to y 1 sin y 2, which is given by again minus 2 log 1 minus x prime sin y 2. So, this is how I generate my uniform normal distribution random numbers. And what are the limits on y 1 and x prime? So, y 1 will go from y 2 will go belongs to your 0 and 2 pi, 0 to 2 pi, and similarly your x prime, that will belong to 0 to 1. So, now if you look one thing, so if my x prime is 1, then this term is always this term becomes log 0. So, and log 0 is undefined. So, that is why I have a open bracket here. So, x prime will be actually less than 0, less than 1. So, now the next question is, can we do some more simplification to this, because you see this involves lot of operations when you try to calculate it. So, it involves estimation of expensive trigonometric functions, the sine and the cosine, then the log, then square root. So, all this takes time to compute in the computer. So, the idea is, can we simplify it further to something which is much more cheaper to compute. So, let us see how we do it. So, some more simplifications. So, to do that, what we assume is, let us do some more change of variables. So, we assume 1 minus x prime is equal to s. So, when x prime is equal to 0, I have s equals to 1, and when x prime equals to 1, I have s equals to 0. So, now if I rewrite, so my x 1 will be equal to minus square root, within the square root minus 2 log s cos y 2, and then x 2 will be equal to minus 2 log s sin y 2. So, this I can rewrite in a slightly different way, which is the following. So, instead of, so if I take y 2, so if you remember as we talked earlier, so y 2 we have to generate from a distribution of random numbers which lie between 0 and 1. So, we need to multiply 2 pi by to this to those random numbers to get y 2. So, rather than doing that, what we can do is we can rewrite this in this fashion. So, x 1 the first part is same as on the left hand side we have, and then instead of cos y 2 we just write 2 pi y 2. In the similar fashion, x2 is equal to root over minus 2 log s, then we have sin 2 pi y2. And the restrictions on s and y2 will be again s should be 0 between 0 and 1, but it should not be equal to 0 and neither it should be equal to 1, because if it is equal to 0 then these x1 x2 becomes undefined, and if it is equal to 1 then we will always get 0 as my two sets of random numbers, which we do not want. So, this is a sort of an open interval we are putting in here, and then y2 now since we have written it as 2 pi into y2. So, we can directly use the random numbers given by my uniform distribution or my pseudo random number generator available in the code. So, that goes between 0 and 1. So, there is some further way to simplify it, and this is what Box-Mueller proposed. So, we will first see what we are doing, what simplification we are doing, and then I will explain to you how this simplification makes the computational cost lower. So, if I look at these two variables, so this I can put in two axes. So, if along the x axis I say this is my s, and along the y axis I have my y2. So, if we look at this, so basically I start from the origin, then I have 1 0, that is the range of x, and what I can do is I can draw a rectangle with these coordinates 0 0, 1 0, 1 1 and 0 1. Okay. So, the idea is the following: what we do is we pick up uniform deviates in. So, the side of each of the square is 1 in an unit square. So, uniform deviates, by uniform deviates what I mean is that the random number which has a uniform distribution. And then we define two variables, let v1 and v2. So, where v1 is my ordinate and v2 is my abscissa. So, what we do is using these two we draw a circle. So, what we have is basically the idea is the following: say we have a circle whose radius is unity. So, okay, this is a bad drawing. So, basically I mean what I mean is this is this side it will be 1 and this side it will be minus 1, 1 0, 1 0, and this coordinate this will again be 0 1 and this will again be 0 minus 1. So, this is my circle whose radius is 1, and we took 2 points v1 and v2. So, such that we have a radius which is given by r square equals to v1 square plus v2 square. So, what it means is, so basically this is my v1, this part here, and then this is my v2, or this normal is my v2, and then I can get the angle theta as the angle sustained by v1 and v2, and this distance from. So, basically this the coordinate of this particular point. Let me use a different color to show the point. So, let us choose green. So, I have this green colored point here. So, the coordinate of this point is given by v1 and v2, and the distance of this point from the origin is sort of you can think of as the radius. So, if you look into these equations, so we need one variable which gives me one number which gives me this one, and the other number is and then we need something analogous to an angle. So, we need a s and we need an angle. So, what we do is, so what they suggested is, let us take s as the square of the distance from the origin of my circle to the point v1 and v2 described by v1 and v2. So, that is v1 square and v2 square. And so, if I think of this as some variable theta, so for these cases the coordinates what I get is I get cos theta will be V 1 by r and sin theta will be V 2 by r. Okay. So, what I now do is basically the following. So, I pick two numbers from my uniform distribution of random numbers, random, or rather in other words random numbers having uniform distribution and lying between 0 and 1. I pick two numbers, I compute S. So, I need to check about the S, because S is crucial, because the value of S can make these two newly generated random numbers to 0, or it can make them to be undefined. So, as per before, so this was the restriction on S. So, what we do is so you choose two random numbers. So, the step is following: you two random numbers V 1 and V 2 from uniform distribution and lying between 0 and 1. Then the second step is compute S. So, the second step is compute S. So, from here what you do is you check S. If my S is equal to 0 or S is greater than or equal to 1. So, what I do is I throw away V 1 and V 2. If these conditions are not satisfied, then else the random numbers which are generated x 1 and x 2 generated using this formula, that we will be using as a new set of random numbers. And if this condition is satisfied, then what you need to do is you need to try the step again. So, this is the whole idea of generating the things. So, at the end of the day, what you have is you take two random numbers V 1 and V 2, which has a uniform distribution, form a uniform distribution and lying between 0 and 1, and then you do this following transformation. So, you generate two new set of random numbers, which is given by minus 2 log r square V 1 by r, and then you have x 2 equals to root over minus 2 log r square V 2 by r. So, these are my new set of random numbers which forms the normal or Gaussian distribution.